What's up, everyone? Today we're talking about delta wings. So what is a delta wing? A delta wing is a triangular shaped wing, and you see them all the time on like fighter jets and this and that. And today we're going to look at two different papers to explain them. The first one is Aerodynamics Investigation of Delta Wing at Low Reynolds Number, and then we'll look at the second one afterwards. So delta wings, they were looked into a lot, probably around in the 50s and 60s starting off with. One really interesting author that did a lot of work on this was a guy called Halmos, and then there's a few others since then, some good ones are Luckring and Hemsch, so check them out. And a delta wing is a pretty interesting type of wing. And this is another article that we look at today. It's called Development of Delta Wing Aerodynamics Research in University Technology, Malaysia Low-Speed Wind Tunnel. And you can find the link in the description. It's an open access paper. And in this, they looked at this triangular shape. So this triangular shape is positioned so that the point is pointing straight into the flow, and then to generate lift, it's the typical flexing up or down, so pitching. And so why is the delta wing important? They first came about because of the idea of trying to produce a lot of lift at high angles of attack. And the reason why they can do that is the method they use to produce lift. It's significantly different to what a typical aircraft wing uses. So it has typically a thin airfoil. So this paper here, this other one I'm reading at the moment, says it is accustomed to have thin airfoil and a sharp leading edge. And there you need both of those to have a good delta wing. And the delta wing can be swept. So this leading edge can be swept at different angles. Each low, moderate, or high swept angle have significant effects on the flow structure over the delta wing. Moderate sweep wing has a sweep angle range from 30 degrees to 50 degrees, which is not optimal for supersonic flight, but well suited for high lift and long range missions, as in the case of unmanned aerial vehicles, so UAVs or MAVs even. Now here it says moderate swept wings, so between 30 degrees and 50 degrees are not good for supersonic flow, but they are good for producing a lot of lift. So why is that? Well, for supersonic flow, the reason why delta wings are quite good for supersonic flow is that, let's say you have this wing here is like this, and then you have some sort of fuselage going through the middle of it. The nose of the wing of the aircraft is going to produce some sort of sonic shock. Now, depending on the geometry of the nose and the thickness and all that, it's going to produce the shock at a certain angle. If you have a moderately swept wing, so let's say it's 30 degrees, often that shock will be sharper than that, so it will impinge on the leading edge of the wings. So that's not good. It's going to produce even more drag that way and have secondary effects. If you sweep the leading edge of the delta wing more, then you may be able to prevent that shock from even impinging upon it, because the angle of the shock is less, so it comes out further. It won't even touch the delta wing leading edges. So that's why at supersonic flows, you want to have, or sonic flows even, you want to have a fairly highly swept wing, highly swept leading edge. It goes on and says that, as I've said, is not optimal. It is optimal for high lift though. So why is a smaller sweep better for high lift? And the reason is for how it produces lift. So delta wings they can produce lift in a regular way, but they also have this other method of producing lift, and it's called a Vortex Lift. And I have a graph here that I show. It's a generic graph which has the alpha, the angle of attack, on the x-axis, and the lift coefficient on the y-axis. And this is a typical lift graph that you see for any airfoil. And the blue line is the lift that a typical airfoil will produce from potential lift. And it's often quite linear at the start, and then you start to get to the point where the flow starts stalling or separating, and then a drop-off in lift occurs from there. And depending how quickly, depending on the wing, this can be a very sharp drop, or it can be a gradual drop, etc. Now, delta wings operate in a slightly different fashion. They produce something called a vortex lift, and I've denoted this with this red line. And one thing you'll notice is that this lift is not that linear compared to the potential lift, and also it doesn't start at the origin. There's an angle of attack that it gets to, and then it will start to kick off. Now we'll go into explaining why that is, but it's important to note that this vortex lift is able to produce more lift than just the regular potential lift. So together, they can produce even more lift than a regular airfoil. There are some caveats in that I'll get to in a second, but that's why delta wings are suited to producing high lift, especially if the leading edges are not that swept. The reason why is because in order to produce this vortex lift, as you may have figured out, you need to have a vortex, hence the name, and you get a stronger vortex with a not as swept leading edge. So what's more, the large area of the wing can reduce the minimum speed of the aircraft. So what that means is because you have a large area, it's a triangle, there's a lot more surface area, which means you just produce more lift overall. It doesn't change the lift coefficient in that sense. It's just that because you have so much more area, the lift equation is half times the density times by the velocity squared times the area times CL, lift coefficient. So just having a higher wing area, you produce more lift. But due to this large surface area, the wing, it has more viscous drag for the same amount of lift, and so it has a lower lift on drag ratio. So a few things here that we should discuss. First of all, the lift on drag ratio. That is a very important ratio for aeronautical engineering and a lot of aerodynamics. It typically denotes how efficient a surface is at producing lift. The greater the lift you produce and the less drag you produce, the higher this ratio, which means that it's producing lift better. Now, the reason why a delta wing has a lower lift to drag ratio, it says here in this paper, it's because it has a more viscous drag because of the surface area. That's part of it. The other reason why is because a delta wing will have a lower lift on drag ratio than a typical wing because it's usually thinner. And so it doesn't produce as much lift usually. A thicker airfoil usually produces more lift. So by having a thin airfoil, and the reason why I needed a thin airfoil is because that helps create the vortex. So provided with a sharp leading edge, the flow gets separated along the leading edge, forming a strong shear layer that spirals up, resulting in a large bound vortex to form, the leading edge vortex. And this is how it's able to produce vortex lift. Now, why is vortex lift so important? Why do we want vortex lift? Why do we want this delta wing? The reason why this vortex lift is so important is not just because you can get a higher lift for the same thickness of airfoil, but because this vortex lift allows you to pitch your aircraft at a much higher angle of attack and still maintain lift. A typical aircraft, for example, if you have a typical airfoil, maybe, you might be able to produce lift up until 15, 25 degrees perhaps. It's not uncommon for a delta wing to be able to produce lift at 40 degrees. So it hasn't even hit stall yet. And that's really impressive because 40 degrees is a very steep angle and you can still produce lift. Why is that? Well, vortex lift is the answer. And the reason why is because these vortices that form, I'll show you a picture of what these vortices look like from this other paper. So this is coming back to this paper that they did some wind tunnel tests on, and then they did some smoke flow vis, and just here. So both of these columns, they show delta wings. They are slightly different. I'll discuss how they are in a second, but I just wanted to show you the vortex, what it looked like. So you can see that these are being pitched at different angles. And then at about 5 degrees, you get this really funky flow here. So it not only goes over the leading edge, it then it's sucked down onto the surface and really sticks to it. And this is the vortex. And then you have this vortex is a low pressure. And so because you have low pressure, the rest of the air going over the wing gets sucked to the surface as well because it has a lower pressure than the free stream. So by having this low pressure on this suction surface on the top side of the airfoil, you're able to keep the rest of the flow attached to the surface for a much higher angle attack. And that's how these vortices are able to allow the delta wing to produce a lot more lift at high angles of attack without stall. So that's really cool. And coming back to this other paper, it says that this vortex lift usually varies approximately to the square of the angle of attack. So that means that it's definitely non-linear and it's sort of almost quadratic-like. What's more, it has been observed by Allen and other researcher, as the sweep angle is increased, the strength of the leading edge vortices decrease, while the size of a vortex formed by a roll-up of the vortex sheet is independent of Reynolds number. So that's true. The strength of a leading edge vortex when you have a delta wing or any swept leading edge does decrease with increasing sweep angle. I've actually done quite a bit of research on this with some other flow control devices, and it's really cool. Like if you have one side which is not as steep as the other side, this side that's not as steep will have a stronger vortex and usually a bigger one as well than the one with a steeper angle. So you can get this imbalance as well. Now, before we go any further, I just want to talk about the atmosphere hawk. This is one of the instruments that we make here at Premier Aerodynamics. This is very important for aerodynamicists, including experimentalists and CFDers and all that. It accurately measures the temperature, barometric pressure, and humidity in your experiments. The reason why this is important is because these three parameters change the density of air on any given day. And these parameters fluctuate enough on a regular day to change the density by maybe 2 to 4%. Now, if you have that error and you don't account for it, or you don't even track it, you cannot change the wind tunnel speed to account for it. You cannot take it into account with your results when you're data processing. And then when you want to use it, for example, for validation purposes, it makes your CFD much more difficult to validate because you're not using the same density of air and you don't even know it. This gets rid of the error for you by measuring these parameters very easily and quickly. And it's done through USB, so you just plug it into your computer and it's ready to go. So make sure you pick one up, link in the description. So coming back to delta wings, let's look at this paper here where they looked at a couple different types of delta wings, as I was saying. On the left, you have something called a blunt edge wing. On the right, you have a sharp edge wing. And as you come down, you have these smoke flows going over both of these over these delta wings at different angles of attack. And at 5 degrees, you start to see this well-developed vortex over the sharp leading edge, but not over the blunt leading edge. And this comes back to this graph that I had here, where at a certain angle of attack, you then start to get vortex lift. Before this angle of attack, which for this paper, for this wing that they looked at, before 5 degrees, you don't really get that lift because you don't have the vortex really forming yet and it's not that strong. On the blunt leading edge, it takes them to a significantly higher angle of attack, so maybe 10 degrees for this to start forming. So this shows us that if you have a sharper leading edge, that's going to produce vortex lift and these vortices much earlier at a low angle of attack. Now, with this, they also found that, not only this, but with other papers and everything with this delta wing, you have this graph. This isn't obviously all of it. So when I was talking about potential lift, I was talking about the stall pattern. What's the stall pattern of the vortex lift? Well, it is quite interesting where in order for the delta wing to stall, you actually need to have something called a vortex breakdown. So the vortex over the actual delta wing just breaks up. It bursts, is what we call it. So it's no longer a coherent vortex core on either side with flow going over it. It just bursts, and that way you don't have this low core pressure region, which is sucking the rest of the flow onto the suction side. And then you start to get stall. And this can happen at quite high angles of attack. Like you can go up to maybe 60 degrees on a delta wing and still produce lift before this vortex bursting occurs. But then once you have this vortex bursting, you need to drop to a long angle attack and then go from there. So delta wings are really cool, and they're used for a lot of different scenarios. As I mentioned, one of the ones was supersonic flow. And I mentioned that with the shock of the nose, if you sweep the leading edges of the wing at a greater angle than the shock of the nose, you can avert some wave drag. But there's also another reason why delta wings are quite good at reducing wave drag at sonic flow and supersonic flows. And that comes down to what's called because it's a thin air fault, it's called the critical Mach number. So the critical Mach number is where the Mach number at which point the flow over an object will become sonic. So with a regular airfoil, let's say regular airfoil and the flow goes over it, we will know that the flow will start to accelerate. So even if your airfoil is at, let's say, Mach 0.9, you're definitely not at the sonic, you're definitely not at Mach 1, you're not at sonic flow, except the flow going over the airfoil is now accelerating. So that's going to start reaching Mach 1. And the point where this does reach the sonic flow is the point where you say this is the critical Mach number. So how do you reduce the critical Mach number? And a very easy way is to reduce the thickness of the airfoil. By doing that, you don't have as much of an acceleration of this flow over the surface. And this is where delta wings come into their own, because by having a thin airfoil, which is what a lot of delta wings are, you can reduce that critical Mach number, which means you can travel at a higher velocity without starting to incur a huge wave drag, a huge drag due to sonic flow. And this is where, as I said, delta wings avert this by having a thin airfoil, so the flow doesn't accelerate as much, and then you can still go a bit higher and velocity and still have a lower drag. So that's the end of this podcast. Hope you enjoyed it. Just we have courses on CFD, experimental and theoretical aerodynamics. Check them out if you want to be a better aerodynamicist. Link in the description. Check out the Atmosphere Hawk. Pick one up. Every aerodynamicist needs one. And our conference, International Aerodynamics Conference, is open. So register for that, and we'll see you there. Peace out.